previous lecture we had solved the hydrogen like atom problem, which was the simplest example of a two body problem, and we were considering two particles M1 and M2. M2 would represent usually the electron, M1 will have a charge of Ze, and the potential energy function was given by minus Ze square by R, where Ze is the charge of the nucleus. And we found that the radial part of the Schrodinger equation could be written as d2u by d rho square plus, since the energy was negative, 1 by 4 plus lambda by rho minus L into L plus 1 by rho square. Now, we studied the small rho behavior of this equation and the large rho behavior. That suggested that we should try out a solution of this form: u of rho is equal to rho to the power of L plus 1 minus rho by 2 times y of rho. Now, there is no approximation here, because I have defined y of rho by this equation. Then we found that if we use this, then y of rho satisfies the following differential equation: rho d2y by d rho square plus 2L plus 2 minus rho dy by d rho plus lambda minus L minus 1 y of rho. Now, if you would recollect, some lectures back we had discussed the confluent hypergeometric equation, which was x d2y by dx square plus c minus x dy by dx minus a of y of x is equal to 0. So, this tells us that this equation is also a confluent hypergeometric equation. Of course, the independent variable is rho now, but c is equal to 2L plus 2, I am sorry, and a is equal to L plus 1 minus lambda. The well behaved, we had studied this equation in great detail. The well behaved solution of this y of x at the origin, you must remember that rho was equal to gamma r, and r is the spherical polar coordinate. So, r goes from 0 to infinity, not minus infinity to plus infinity. So, r goes from 0 to infinity. So, y of x was one of the solutions is f11, the well behaved solution is ACX, and this is the well behaved solution is y of x is equal to f11. This is the confluent hypergeometric function, and the series representing that is very easy to remember: 1 plus a by c x by 1 factorial plus a into a plus 1 divided by c into c plus 1 x square by 2 factorial plus a into a plus 2 plus 1 a plus 2 and so on, c into c plus 1 into c plus 2, etc. x cube by factorial 3 and so on and so on. Now, as I had discussed earlier, if A is equal to C, then this is just the series e to the power of x. So, although the infinite series is convergent, but it blows up at infinity as e to the power of x. I repeat, although this infinite series is convergent, it blows up, it converges to a very large value for large values of x. So, in fact, the asymptotic form of f1c, this is x to the power of a minus c into e to the power of x. Now, you may recall that my u rho function was rho to the power of L plus 1 e to the power of minus rho by 2 y of rho. Now, at large values of rho, this will behave as e to the power of rho. So, this multiplied by this will become e to the power of rho by 2. And so, although the infinite series is convergent, the wave function will blow up. And that cannot happen. The wave function can, otherwise it will not be normalizable. So, it can be reduced to a polynomial only if a is 0 or minus 1 or minus 2, etc. So, we put this as minus n of r, where n of r is known as the radial quantum number. Radial quantum number. So, therefore, we have, if you recall that we had here in this paper the differential equation that we had obtained was the confluent hypergeometric equation with C is equal to 2L plus 2 and A is equal to L plus 1 minus lambda. So, we have now shown that for the solution to be well behaved, A must be 0 or a negative integer, or I write that as minus NR, and since A is equal to L plus 1 minus lambda, so this is equal to minus NR. So, please see this, I take lambda to this side and NR to this side. So, I get lambda is equal or is equal to L plus 1 plus NR, where NR goes from 0, 1, 2, 3 to infinity. So, this is because of L also, if you recollect, is equal to 0, 1, 2, 3, etc. So, this I write is equal to n, which is known as the total quantum number. And n can only take values 1, 2, 3, 4, etc. So, this is my total quantum number. So, we have proved that for the wave function to be well behaved, that is for the wave function not to blow up at infinity, lambda must be equal to an integer. And if you recall that lambda was equal to 2 mu e square by h cross gamma. So, we write this down as, please see this, lambda was equal to 2 mu z e square by h cross square gamma. This must be equal to n, and 2 mu e by h cross square gamma square we had put equal to minus 1 by 4. So, gamma square was equal to minus 8 mu E by H cross square. So, if I square this is very easy, 4 mu square Z square E4. Okay. Now, I will do one more simplification. E square by H cross C is equal to alpha. So, this will be E square square. So, therefore, alpha square H cross square C square divided by, I have squared this. So, 4 mu square Z square alpha square H cross square C square divided by H cross to the power of 4 is equal to n square gamma square, n square gamma square. So, gamma square is minus 8 mu E by H cross square. So, please see this, we have to do this little carefully. So, H cross square multiplied by H cross square by H cross 4, these two terms will cancel out. 1 mu will cancel out with 1 mu, and 4 divided by 8 is n 2. So, I will get E is equal to E n is equal to minus 4, this becomes 2. So, 2 n square mu Z square alpha square C square. You must check the dimensions. Alpha is a dimensionless parameter, Z square is a dimensionless parameter, mc square, as you know from Einstein's equation, mc square is the energy. So, this is energy. So, that is all right. So, this quantity is so therefore, these are the discrete energy states of the hydrogen atom, and it is a remarkable triumph of the Schrödinger equation. Schrödinger obtained this in his very first paper in 1926. He wrote down the Schrödinger, he wrote a series of 3 papers on, and which gave birth to the field of quantum mechanics or wave mechanics. And in the first in one of the papers, he introduced the Schrödinger equation, and then he solved it for the hydrogen atom problem, and he obtained the discrete eigenvalues from the solution of a differential equation. And this is considered to be one of the greatest triumphs of quantum mechanics. From the solution of a differential equation, one obtained the energy eigenvalues of the hydrogen atom, which compared extremely well with the experimental data, the Balmer series, the Lyman series, and the Paschen series. So, here you can see mu is the reduced mass. So, as I had mentioned that for the hydrogen atom, Me is the electron mass, Mp is the proton mass. So, for the hydrogen atom, mu h is equal to, you may note, write it down if you feel like, Me Mp by Me plus Mp, which is 9.1045 into 10 to the power of minus 31 kg. And alpha, as we know, is about 1 over 137. C is approximately 3 into 10 to the power of 8 meters per second, and N can take values 1, 2, 3, and for the hydrogen atom Z is equal to 1, for the deuterium atom Z is equal to 1, because the hydrogen atom is 1 proton and 1 electron. The deuterium atom is 1 proton and 1 neutron and the electron. So, here also Z is equal to 1 for the deuterium atom. For the helium atom, the nucleus consists of the alpha particle, 2 protons and 2 neutrons. So, Z is equal to 2 for the helium plus. Singly ionized helium atom has Z is equal to 2, and of course, the mass of the nucleus is slightly different. So, the reduced mass is different. So, therefore, we will have so these are the energy eigenvalues, and if you substitute the values of mu that I wrote down and alpha that I wrote down and C etc., and if I assume Z to be 1, so you get the lines energy levels corresponding to the hydrogen atom. So, in a transition, say from n is equal to n1 to n is equal to n2, when an atom makes a transition characterized by the total quantum number n1 to a total quantum number n2, a photon is emitted corresponding to the appropriate frequency or wavelength. So, when n2 is 1 and n1 is 2, 3, 4 etc., you get what is known as the Lyman series. When n2 is 2 and n1 sorry, n1 is 3, 4, 5, 6, 7, 8 etc., you get the Balmer series, and n2 is equal to 3 and n1 is 4, 5, 6 etc., then you get what is known as the Paschen series. These are the different series in atomic spectra, and similarly you will obtain the series for deuterium atom, the helium singly ionized helium atom and the lithium atom. Now, from this, so we can calculate if one makes a transition from n1 to n2. So, let me write it down that E n1 is equal to minus mu z square alpha square c square by 2 n1 square, and E n2 is equal to minus mu z square alpha square c square by 2 n2 square. So, if I have a transition from n is equal to n1 to n is equal to n2, so you must write down. So, the frequency of the wave light emitted will be IGNOU or hc by lambda is equal to E n1 minus E n2. So, this will be minus sign. So, this will be mu z square alpha square c square by 2 1 over n2 square minus 1 over n1 square. So, the wavelength of the emitted light will be 1c will cancel out. So, you will get 2h by mu z square alpha square into 1 over n2 square minus 1 over n1 square raised to the power of minus 1. Now, if I consider, so if I consider two atoms, one is the deuterium atom and the other is the hydrogen atom. As I mentioned, the hydrogen atom consists of one proton and one electron, and the deuterium atom consists of one proton and one neutron. So, for both the cases Z is equal to 1, but since the mass of the nucleus is larger here, so the reduced mass is ME m of the nucleus divided by ME plus Mn. So, because mass of the nucleus is larger here, the reduced mass in the two problems will be slightly different. And in fact, what was observed was that in one of the transitions, in n equal to 3 to n equal to 2 transition, which is in the Balmer series, I leave it as an exercise for you to calculate. The wavelength that is emitted was 6.5647. This is in the visible region, 10 to the power of minus 5 centimeter, and 6.5629 into 10 to the power of minus 5 centimeter. This is for the hydrogen atom and this is for the deuterium atom. And it was Urey, the chemist, in 1932 who discovered the presence of another line in the spectrum of hydrogen. They had similar lines as the hydrogen atom, but they were slightly shifted. He measured that carefully, and this was in the year 1932 when quantum mechanics was already discovered. And he said that this is an isotope of hydrogen, and he calculated the reduced mass, and from which you can calculate the mass of the deuterium nucleus. And he said this must be due to an isotope of hydrogen. So, it is through spectroscopy that the heavy water or heavy hydrogen was discovered. So, you have here for example, the Rydberg constant, you see, the energy in spectroscopy is usually measured in centimeter inverse. So, we write this as a term value is equal to E n by h c, E n by h c. So, if I divide by h c, so you will get minus mu z square alpha square c square by n square divided by h. So, the dimension of this is centimeter inverse, and this quantity is known as the Rydberg constant, that is minus z square r y r divided by n square. So, where r is known as the Rydberg constant, which is equal to mu alpha square c square by h. And because of the slight difference in the reduced mass, the value of the Rydberg constant is slightly different. For the Rydberg constant is 1096, you may write it down if you feel like, 109677.58 centimeter inverse for the hydrogen atom, 109707.56 centimeter inverse for the deuterium atom. Both of them are z is equal to 1, z is equal to 1. This is z is equal to 2 for the helium plus atom, and this is doubly ionized lithium atom, in which this is z is equal to 3. And here for example, so for the helium plus atom, you have 2 protons and 2 neutrons, and because of 2 protons, the neutral helium atom consists of 2 electrons. So, if you take 1 electron out, then you will have the helium plus atom. Similarly, for 3 lithium 7, you have 3 protons and 4 neutrons. This is one of the isotopes of 3 protons, and so the mass number is 7, the atomic number is 3. So, for the neutral lithium atom, you will have 3 electrons. If you take 2 of them, you ionize 2 of them, then you will obtain a single electron atom, but z is equal to 3. But since the mass is much heavier now, the reduced mass is slightly larger, and which results in a slightly different value of the Rydberg constant. So, we have now obtained the solution of the Schrodinger equation and the eigenvalue spectrum correspond to the single electron atom, in which the potential energy function is given by minus Z E square by R in the CGS system of units, and in the MKS system of units all that I have to do is replace E square by Q square by 4 pi epsilon naught. That is it. And Q is the charge of the electron in coulombs, and Z is the charge of the nucleus. So, that completes the energy eigenvalue spectrum of a 1 electron atom. Now, we go back to the radial part of the Schrodinger equation, and we have u of rho as rho to the power of L plus 1 e to the power of minus rho by 2 F 11 A C rho, and A was equal to L plus 1 minus lambda, C was equal to 2 L plus 2, and this is rho. You may recall that R of R or R of rho was equal to u of rho by rho. So, the radial part of the wave function was equal to rho to the multiplied by a normalization constant, rho to the power of L e to the power of. This is the rigorously correct wave function for the hydrogen atom. How would I determine? So, these functions are so lambda was put equal to n. So, let me write it down. This is the normalization constant, rho to the power of E L minus rho to F 11 L plus 1 minus n 2 L plus 2 into rho, and the normalization constant is that is equal to, that is little difficult to obtain, it is a little cumbersome. I would not say 2 L plus 1 factorial divided multiplied by n plus L factorial divided by 2n into n minus L minus 1 factorial. The hypergeometric functions are much easier to handle than the associated Laguerre polynomials, which is mentioned in most of the books. Now, let us suppose that I want to find out, you give me any value of n and any value of L. So, let me find out for n is equal to 5 and L is equal to 4. So, you can now see that L plus 1 minus n. So, this function will be f11 will be 0, 2L plus 2 will be 10 into rho, but if A is 0, this is 1. So, I can immediately write down within a multiplicative constant R54 by of rho is equal to some normalization constant rho to the power of 4 e to the power of minus rho by 2. If you do not want to remember this cumbersome formula, then you can immediately determine the normalization constant by saying that R n L of R mod square, this is the normalization constant, R square dr from 0 to infinity must be equal to 1. So, you see the complete wave function, psi of r theta phi is equal to r n L of r y L m of theta phi. This you must remember. This is normalized. So, in Cartesian system of coordinates, the volume element is dx, dy, dz. In the spherical polar coordinates, the volume element is r square dr sin theta d theta d phi. So, the normalization condition is mod psi square, this whole volume element r square dr sin theta d theta d phi, triple integral. R goes from 0 to infinity, theta goes from 0 to pi, and phi goes from 0 to 2 pi. This must be equal to 1. This is the normalization condition. So, if I take the r part outside and the theta part outside, so the normalization condition for the spherical harmonics is modulo theta going from 0 to pi and phi going from 0 to 2 pi modulus of y L m theta phi square sin theta d theta d phi is equal to 1. This is the normalization condition for the spherical harmonics. And for the radial part, therefore, for the radial part, you will have integral 0 to infinity r n L mod square, actually they are all real. So, it does not, r square dr is equal to 1. This is r and not rho. So, we had here for example, r 5/4 of r, I hope I have done it correctly. So, r 5/4 of r is equal to n rho to the power of 4 e to the power of minus rho by 2. So, so rho is equal to gamma r. So, you can see if I multiply by gamma cubed and then you have 1 over gamma cubed n square rho to the power of 8, this is RNL square, e to the power of minus rho and then rho square d rho. From 0 to infinity. So, this is 0 to infinity rho to the power of 10 e to the power of minus rho d rho is equal to 1. So, this is 10 factorial. So, n square is equal to gamma cubed into 10 factorial, or n will be gamma to the power of 3 by 2 square root of 10 factorial. So, if you want to do if you want to calculate any radial part of the wave function, it is really very simple. So, let me give you another example. So, as I had said, r n L of r is equal to n rho to the power of L e to the power of minus rho by 2 f 1 L plus 1 minus n 2 L plus 2 rho. Now, let me calculate for r 4 2 of r, just as an example. So, n is 4 and L is 2. L is 2. So, let me first calculate what is this function. So, this the hypergeometric function is L plus 1 minus n, L plus 1 minus n, that is 2 plus 1, that is 3 minus 4, that is minus 1, and 2L plus 2, that is equal to C is equal to 4 plus 6 into rho, and this is 1 plus A by C, that is minus 1 by 6 into rho by factorial 1, then A is minus 1, A is minus 1. So, A into A plus 1, so that is 0. So, this will be just 1 minus rho by 6. So, R 4 2 of R will be equal to n, L is 2, this is e to the power of minus rho by 2 minus rho by 6. Confluent hypergeometric equation function gives you very readily the complete radial part of the wave function, provided you, of course, you must be given the values of n and L. So, this completes the analysis of the hydrogen like atom spectrum. What I would like to do, or before that, let me summarize. So, therefore, you will have for V, the summary is V of R for a minus Z square by R, and the wave function will be one describing the translational motion of the total hydrogen atom or hydrogen like atom, the total motion of the center of mass as a free particle, and the internal motion. So, for that we had to solve in terms of the radial coordinate 2 mu by h cross square E minus V of R, that is plus Z square by R psi of R theta phi, and then psi of R theta phi was equal to R n L of R y L m of theta phi. These are the spherical harmonics, and this is the radial part of the wave function, and the radial part of the wave function is R n L of R is equal to n rho to the power of L e to the power of minus rho by 2 f 1 L plus 1 minus 2 L plus 2 into rho, and we have already discussed, and finally the energy eigenvalues are E is equal to E n minus Z square C square alpha square mu by 2n square. These are the energy eigenvalues of the hydrogen like atom problem, and we discussed that that you can use this formula to calculate to obtain the spectra associated with the hydrogen atom, deuterium atom, singly ionized helium atom, doubly ionized lithium atom, and so on. There is one thing that I would like to mention, that we have considered the negative energy states. Now, the positive energy states, you see, if I have a proton sitting here and an electron comes from a very far distance and gets scattered. So, those are the E greater than 0 states. So, even in planetary motion, you can have an object which comes near the sun and gets scattered, and then there is Earth which is bound to the sun, which is rotating in a orbit. So, even in the hydrogen atom, in both cases the we have inverse square law. In quantum mechanics also, there are two types of solutions. One corresponds to E less than 0. So, those are the bound state solutions. Bound state solutions, and for E greater than 0, those are the scattering states. For every problem, scattering solutions. Even in the neutron proton problem, you have a bound state problem in which the neutron and proton are held together and you find the discrete energy states. On the other hand, you can have a neutron proton scattering problem, which is one of the most important problems in quantum mechanics, that you have a neutron beam coming in here and getting scattered by the proton. So, this is known as the neutron proton scattering. So, those correspond to the continuum solutions E greater than 0. In one dimensional quantum mechanics, you had remember that we had the potential well problem. Now, in this potential well problem, you have two types of solutions. This is, let us suppose, 0 and V 0. For E lying between 0 and V 0, you have bound state solutions, where the particle is confined within the well. You have wave functions which are exponentially decaying here. So, they are tightly confined here. They are localized, and the energy eigenvalues are discrete. So, these are known as the discrete bound states. Discrete bound states. And then you will have E greater than 0 solutions. These are the scattering states, and they form a continuum. All possible values of energy are allowed, and so therefore, you will have this, an incident beam coming in, part of it is reflected and part of it is transmitted. So, we will have two types of solutions. In the hydrogen atom problem, or what we were going to discuss is the neutron proton problem, we will just now confine ourselves to the negative energy solutions, in which you have what are known as the bound states. Now, let me just start and then we will continue with that in our next lecture. We consider the deuteron problem. This is the fundamental problem in quantum mechanics, in nuclear physics, the deuteron problem, in which you have a neutron and proton. Now, scattering experiments suggest that they have all, because neutron is an uncharged particle, they have no interaction beyond a certain distance. So, there is a model in which you have V is equal to infinity at r is equal to b. So, something like this, that this is the potential as a function of r. So, at r is equal to b is an infinite potential, and then it is minus V 0 from r equal to b to a plus b, and then it is 0 beyond this. So, that this is known as the hardcore potential, in which the neutron and the proton cannot be closer than the distance b. So, let me write down the radial part of the Schrodinger equation. So, d2 u by dr square plus 2 mu by h cross square E minus V of r minus L into L plus 1 h cross square by 2 mu r square. U of r is equal to 0. I assume consider the L equal to 0 problem just to make life simple, and then you must always remember that R goes from 0 to infinity, not minus infinity to plus infinity. So, we will consider once again the negative energy states of the problem, and so E is negative and L is 0. So, we consider this as example 2. The deuteron problem. So, you have d2u by dr square plus 2 mu by h cross square. E is negative. So, I write this down as V of r is equal to V0 minus V0. So, V0 minus mod of E. I hope you understand. U of r is equal to 0. This is for r less than a plus b less than b. In this region, V of r is assumed to be minus V0, minus V0. So, for r greater than a plus b, you will have d2 V of r is 0, this term is 0, but E is assumed to be negative. These are the bound state problems. So, d2u by dr square minus 2 mu mod E by h cross square u of r is equal to 0. So, this is for r greater than a and b. So, in the region r greater than a plus b, I write this as d2u by dr square minus kappa square u of r is equal to 0, where kappa square is defined to be equal to 2 mu mod E by h cross square. So, as we all know, this has two particular solutions. So, this solution will be u of r will be say c e to the power of minus kappa r plus d into e to the power of plus kappa r. This will exponentially blow up, this will exponentially, and therefore, the wave function will not be normalizable. So, we must choose d is equal to 0. So, in the region r greater than a plus b, the wave function will be u of r is equal to c e to the power of minus kappa r. In the region b, for r lying between a plus b and b, this we write as d2u by dr square plus k square u of r is equal to 0. So, where k square is equal to 2 mu by h cross square V0 minus mod E. So, the solutions are very simple. A sin kr. So, I write this as r minus b plus b cos of k r minus b. Just I have introduced this b just for the sake of simplicity. Now, at r is equal to b, there is an infinite potential. So, the wave function has to go to 0, because the the interparticle distance cannot be less than b. That is what this potential physically implies. This is known as the hardcore potential, where the neutron and the proton cannot. This is one of the models, and no one really knows the exact potential energy distribution between the neutron and the proton, but this is a simple model which is quite accurate, that for distances, that the distance between the neutron and the proton cannot be less than b. So, at r equal to b, the wave function must be 0. So, at r equal to b, the wave function is 0. So, u at r equal to b must be 0. So, if I put r equal to b, this term goes 0. So, 0 is equal to, this is cos of 0. So, that is b, cos of 0 is 1. So, this term b is 0. So, you have u of r is equal to a sin k of r minus b. So, therefore, we will have for r less than a plus b less than b, u of r is a sin k r minus b. For r greater than a plus b, u of r will be c into e to the power of minus kappa r. So, we must have the wave function continuity of the wave function of u of r at r is equal to b will give me a r equal to b plus a, sorry, continuity at r equal to a plus b will give me a sin k a is equal to c into to the power of minus kappa a plus b. Similarly, if I take the derivative continuity of u prime of r, so this will be k a cos k r minus b, and at r equal to a plus b it will be cos k a minus c kappa e to the power of minus kappa a plus b. So, if I divide this equation by this equation, so I will get minus k cot k a is equal to kappa. So, if I multiply both sides by a, so I will get something like this. So, this is an equation which is similar to what we had encountered earlier. So, minus xi cot xi is equal to eta, where xi square is equal to k square a square, and this is equal to 2 mu by h cross square v 0 minus mod e by multiplied by a square, and eta square is equal to kappa square a square, and that is equal to 2 mu mod a e square by h cross square. And if I add these two, then I will get, if I add these two equations, xi square plus eta square, then you can see the mod e term cancels out. So, you get 2 mu v 0 a square by h cross square. This I put equal to alpha square. For a given potential, for a given reduced mass, for a given radius, and of course, Planck's constant is a constant. So, therefore, this gives me that eta is equal to under root of alpha square minus xi square. So, therefore, this term will be just the similar thing that we had experienced in our one dimensional case. So, for a given value of alpha, we have to solve this transcendental equation and obtain the discrete eigenvalues. So, minus xi cot xi will have something like this. This is at pi, that it will become infinite, and this is pi by 2, and then you will have something like this, and the right hand side will be the quadrant of a circle, and the points of intersection will give me the eigenvalues. We will specifically consider a profile which closely corresponds to the deuteron problem, and then we will solve the equation and obtain the eigenvalues of the problem. Thank you.